Welcome to The Explainer. Today, we're tackling a challenge that, well, literally every high school math teacher knows all too well: building the ultimate engaging math lesson. Specifically, we're diving into a masterclass approach for teaching quadratic equations. We're going to completely transform how we think about presenting this foundational math concept. We're moving away from rote memorization and towards a beautifully designed, highly intentional learning experience.
It's the ultimate question, right? Why do students absolutely dread quadratic equations? You know the moment. It's that point in a student's mathematical journey where numbers suddenly vanish, the alphabet completely takes over, and this collective groan just echoes through the classroom. They look up at the board, see a jumble of x squareds, a's, b's, and c's, and completely lose the plot. But it really doesn't have to be this way. And fixing it actually starts way before we write a single equation on the board.
Okay, let's dive right into this by looking at some insights from Gemini, an AI assistant mapped specifically to math pedagogy. It reminds us that strong pedagogy is our ultimate solution here. Quote, "Setting clear, measurable goals is the best way to ensure your students don't get lost in the algebra." If we want students to navigate the really complex mechanics of quadratics, we have to map the destination perfectly from the get-go.
To get there, here's our roadmap for today. 1. Setting clear objectives. 2. Visualizing completing the square. 3. Deriving the formula. 4. Avoiding common mistakes. And 5. Designing engaging presentations.
Starting off with Section 1, Clear Objectives, Setting the Stage.
Now, what's really interesting here is how we can frame the entire lesson structure using Bloom's taxonomy. We're not talking about passive goals. These are 6 active, highly measurable verbs. First, we want students to define standard form coefficients. We want them to solve using multiple methods. They need to examine the discriminant, verify their solutions by substituting roots back in, assess the absolute best solving method, and finally, model real-world scenarios, like projectile motion. Bringing in this active vocabulary ensures our lesson is purposeful from minute 1.
Moving right along to Section 2, Visualize the Square, a Geometric Approach.
To really nail this, we've got to channel the sheer enthusiasm of legendary math educator Eddie Wu. As he points out, the absolute mind-blowing realization for students is that we're dealing with literal physical squares. He says x squared literally means it's a square and its side length is x. It's not just some abstract mathematical operation, it's a beautiful geometric construction. When students realize they're actually building a physical square, the algebra suddenly makes total sense. It's a real game changer. Let's walk through this visual metaphor step by step. Imagine you have an equation with x squared plus 10x. First, you picture an actual square with side length x. That's your x squared. Then, you have a rectangle with side lengths 10 and x. That's your 10x. Now, step 2 is basically a magic trick. You slice that 10x rectangle perfectly in half, which gives you 2 rectangles of 5 by x. For step 3, you take those 2 5x rectangles and build them right onto the sides of your x squared square. But wait, now you have an incomplete shape. Step 4, you look at that missing corner piece. It's a 5 by 5 space. So what do you need to add to complete the whole shebang? 25. You are literally completing the square. It turns this abstract, confusing algorithm into a super simple puzzle.
All right, Section 3, Derive the Formula, Rigorous Mechanics.
And this brilliantly illustrates the kind of rigorous framework we need to establish. We're looking at a derivation breakdown from Graham Henderson at Crystal Clear Mathematics. Actually, let's be honest, looking at the full derivation all at once, well, it can induce absolute panic in a classroom. The key to teaching this isn't just showing the math, it's really about structuring the practice of the math. We absolutely must chunk these heavy algebraic milestones into clean, sequential steps. Otherwise, the audience just gets completely overwhelmed. Step 1, divide by a to make it a monic quadratic. Step 2, subtract c over a to move the constant to the right-hand side. Step 3, we apply that cool completing the square technique we just learned by adding the square of half the middle term. Step 4, take the square root of both sides. And finally, Step 5, isolate x. By presenting it this cleanly, we give students a ladder to climb rather than a massive wall to scale. But here's the thing, just knowing the steps isn't enough. How do they actually memorize this complex derivation? Henderson notes there are 2 distinct practice methods required here. First up is mass practice. This means setting aside time for intense, daily focus, without any distractions, practicing the derivation until it's completely obvious and you can do it lightning fast. But then, to make it actually stick long-term, you've got to transition to distributed practice. This is spaced repetition over time. You literally set a calendar reminder to practice it just before you're likely to forget it. It's an absolutely crucial strategy to ensure the learning actually lasts.
Which brings us to Section 4, Common Mistakes, Troubleshooting Guide. Let's quickly map out the absolute most common mathematical pitfalls and their immediate practical fixes. Number 1. Sign errors when substituting into the formula. The simplest solution? Always use parentheses around substituted values, especially the negative ones. Second, factoring errors. For this one, teach them to always check for a greatest common factor before even trying to factor the quadratic. Third, forgetting to simplify the final answer. Remind them to reduce those fractions fully. And fourth, ignoring special cases. Look, if there's no linear term, or b equals 0, there's no way you should use the full formula. Just isolate x squared. These super simple fixes save literally hours of student frustration.
So, a really crucial point here is often found in the discriminant, b squared minus 4ac. This tiny little piece of the formula determines the entire nature of our roots. If it's greater than 0, 2 real solutions. Equal to 0, 1 real solution. Less than 0, 2 complex solutions. A major pitfall for students is seeing a negative discriminant and immediately declaring no solution. As educators, we have to clarify that complex solutions are perfectly valid solutions. They just aren't real numbers. Getting them to calculate the discriminant first gives them a massive strategic advantage.
And finally, Section 5, Designing Engaging Presentations, Visual Packaging.
Believe it or not, the colors you choose for your slides matter immensely for student comprehension. Based on updated 2026 presentation design principles, we need to follow a few foundational rules. First, keep contrast strong. Dark text on a light background is always a safe bet. Second, limit your color system. Too many colors just create visual noise. Third, design for all audiences. You've got to be mindful of color blindness, so definitely don't rely solely on red and green to convey vital info. And fourth, match your color tone to the purpose of your lesson. A clean slide flow keeps attention exactly where it belongs, on the math.
Think of your ideal color palette kind of like a pie chart. The largest slice by far is your dominant background color. The medium slice represents your 1 or 2 text colors, and the smallest slice, that's your single accent color, and it should only be used for highlights or key data points. Limiting your color system to these 3 specific roles dramatically reduces visual clutter and really boosts student retention. If a presentation ever looks messy, it's usually because this proportion is completely out of whack.
Now for a longer, pretty intense subject like quadratic equations, experts highly recommend a specific approach, the soft educational palette. We're talking warm cream, soft brown, dusty blue, and light sage. Why these? Well, because the lack of extreme, blazing contrast drastically reduces visual fatigue. A neon background might look super cool for a quick 5-minute pitch, but for a 45-minute math lesson, it's just exhausting for the eyes. Soft tones keep the environment approachable, calm, and focused.
And just like that, we've reached the end of our roadmap. We've seen how intentional objectives, visual geometry, perfectly structured derivation steps, proactive troubleshooting, and intelligent slide design all come together. So the question I want to leave you with today is this. Will your next math lesson just be a rote exercise of symbols on a whiteboard, or will it be a beautifully designed masterclass? By taking these ideas and structuring your visual presentations with real purpose, you have the power to completely change how your students experience mathematics. Thanks for joining me on The Explainer.